Okay, thank you for the intro. Thank you for being there. Hey, everybody. So my name is Juraj, and I'm a postdoc at University Bochum. And in parallel, I'm working for our company, Hackmanit GmbH, where we do pen testing and security analysis and so on. So today I'm going to talk about attacks on TLS and how can we find them automatically. It's a paper that was published like 1 month ago at CCS. It's a scientific conference. Okay, so probably everybody knows that, or we can say that transport layer security, or TLS, is the most important security protocol that we use, or cryptographic protocol. It is used to secure HTTP, SMTP, IMAP, or so if you are going to a website and see this green log and want to log in there, then we are using HTTPS, so TLS. Currently, we are using in most of the modern browsers TLS 1.2 version. But before we got there, there was a longer way. So it already started like in 1994 as Netscape released their SL version 2 called Secure Socket Layer. This version was deliberately broken and vulnerable to specific attacks. So directly afterwards, they came with a new version called SL version 3. This was released publicly, and there is already a standard. And this version, SL version 3, was later in 1999 adopted by IETF and was officially made to a standard called transport layer security. So in 1999, we got transport layer security version 1.0, and with the time we added some new features to transport layer security. So we got TLS 1.1, 1.2 in 2006 and 2008, which included some elliptic curves, new extensions, and so on and so on. And now we are working with TLS 1.3. So TLS 1.3 is currently standardized and deployed on some servers from Cloudflare, or it's developed by Mozilla and Chrome. So in parallel, so TLS became more and more important. So in parallel, it was getting more interesting for attackers and researchers. So the first attacks were published in 1996, maybe, when Wagner and Schneier analyzed SL version 3 and showed how it is vulnerable to specific attacks and how SL version 2 was vulnerable. In 1998, we have seen Bleichenbacher's attack. It's also called million message attack. Maybe you know, some of you know that it was the basis of the known drone attack. In 2002, we saw padding oracle attacks by Wodenai, which are also deployed to TLS. And with the time, TLS got more and more interesting. So in 2011 or 12, we could see the first attack with their names like Beast, Lucky 13, Breach, and so on and so on. And in 2014-15, also the first attacks that had their names and logos like Heartbleed, ELE, CCS, or Drone. Okay, so TLS is getting more and more important. And the question is, so there are many attacks getting released. And from a security perspective, or from a pen tester perspective, there's a question, so how can we test these attacks? So if they are released, how can we write proof of concepts? How can we validate whether the implementation is vulnerable to these attacks? Or maybe better, can we find such attacks automatically? Can we find new attacks automatically? So we did a brainstorming on this, and we found out that there is a good approach on this that works, and that was published a few years ago, and consists of 3 steps. So in the first step, you collect TLS libraries, like OpenSSL, LibreSSL, and so on. Then comes the second phase, and in the third phase, you profit. Okay, so this research was published in the second South Park season and was adapted to collecting underpants. Could be also applied to TLS libraries or to other protocols, but we wanted to get better and get a scientific publication. So we concentrated on the second step. So what's in the second step? And what are our contributions? So we designed a flexible TLS framework for fuzzing, testing, writing attacks. This is called TLS attacker. And TLS attacker allowed us to find high-impact vulnerability in OpenSSL, for example, or additional vulnerabilities in Botan, Matrix SSL, and other libraries. It is released as an open source framework available at GitHub. Okay, so in this talk, I will give an overview of TLS attacker design and how can you use it to make proof of concepts attack, how can you fuzz TLS implementations. And for this, I will first introduce briefly the TLS protocol, then give an overview of some interesting attacks which led to design of TLS attacker, and then I will show how to fuzz implementations and present some results. Okay, let's start with the TLS protocol. So in order to encrypt the traffic, TLS traffic, first of all, what we do is a so-called TLS RSA handshake, where we exchange the keys. And this works as follows. So if you have a client who wants to connect to a server, he first sends a client hello message where he proposes the list of extensions, cipher suites he is speaking, and so on and so on. The server responds with the server hello message where the chosen cipher suite is used, extensions, and so on. There is a certificate which contains the public key and then server hello done message. Afterwards, the client sends a client key exchange message. This client key exchange message takes the public key, encrypts a so-called pre-master secret, sends it to the server. Afterwards, the client sends chain cipherspec and finish message where he confirms, I know this pre-master secret, I can derive the keys. The server decrypts the pre-master secret and issues chain cipherspec and the finish message. And after this, both client and server share keys, and they can exchange encrypted application messages. Okay, so this is the basic TLS RSA handshake. However, TLS is complex. There are different TLS versions, also old versions of SSL, so there's TLS 1.0, 1.1, 1.2. They are using different cryptographic primitives like RSA, elliptic curves, AES, new Chacha poly algorithms, or post-quantum crypto like New Hope. There are different extensions to TLS that are standardized in different IETF standards, and these result also in different protocol flows. So for example, if we take a look at this basic TLS protocol flow, then this is just an example. So if we are, for example, using ephemeral cipher suites like elliptic curves, then the server sends an additional server key exchange message. If the client authenticates himself, then it sends a certificate and certificate verify message. And there is also a possibility to send heartbeat messages after the handshake was established. So the TLS protocol can get very complex with everything what we got. So this complexity resulted also in these attacks that we could see in the last years. And I'm not going to talk about all these attacks. I will just give a brief overview of 3 attacks that are interesting maybe or that motivate our TLS attacker. There are padding oracle attacks, Heartbleed, and early CCS. So just to give you an overview. So let's start with early CCS. So the early CCS works as follows. So imagine we have this handshake with TLS RSA, and we have an attacker who is doing man-in-the-middle attacks. So what he can do, he can, in older OpenSSL versions, what he can do, he can, for example, remove the client key exchange message. The client key exchange message contains the encrypted pre-master secret. If this client key exchange message is not sent to the server, then the server computes the master key or the keys based on the 0 value buffer. In specific situations, I'm not going into the details, this could result into man-in-the-middle attacks in specific OpenSSL versions, and so one can do man-in-the-middle. This attack led to further research on state machine attacks. In 2015, we saw two papers by Bardush et al. So, for example, they showed how to execute freak attacks, or there were other state machine attacks presented by Deruta and Paul. Then we have the famous Heartbleed attack. So, Heartbleed attack targets the heartbeat extension. The heartbeat extension was introduced because of DTLS. DTLS is TLS executed over UDP. UDP is not reliable, so we want to have some mechanism to find out whether the TLS server is still running or accepts our connection. So what the client can do, he can send a so-called heartbeat message. There is a string like DeepSec. This string is 7 bytes long, so it prepends 7 byte length. And the server takes this message, DeepSec, okay, I need to respond with 7 bytes, and responds with this string. The attack worked as follows. So it was a buffer overread attack. So what the attacker can do, he can define a string DeepSec with the length 1000, for example. What the server does, he attempts to respond with 1000 bytes, but DeepSec string is only 7 bytes long, so he overreads the buffer and responds with maybe some private keys or something like this. Okay. And then we have some padding oracle attacks or cryptographic attacks in general. So, for example, padding oracle attacks are adaptive chosen ciphertext attacks. I'm not going into details how they work, but imagine that the client sends a ciphertext to the server. The attacker eavesdrops this message and modifies it somehow, modifies the padding, which is encrypted, sends it to the server and uses it as an oracle. This is why they are called padding oracle attacks. And the oracle answers with valid or invalid based on the padding validity. Yeah, and the attacker repeats this several times, and afterwards he can decrypt the ciphertext. Okay, so this is the basic idea behind the padding oracle attacks introduced by Wodena in 2002, but it is also the basic idea behind Bleichenbacher's attack from 1998. Okay, so we could see that TLS attacks are not only crypto attacks. We have attacks on TLS state machines like Freak or early CCS that target the complex state machines and TLS implementations. And we have some buffer overflows or overreads attacks on TLS implementations like Heartbleed. But Heartbleed is not just an example. So for example, in September, we got 2 releases of OpenSSL. The first release targeted one high-level vulnerability in OpenSSL, which was then patched, and a day afterwards they found out that this patch introduced a critical vulnerability, so there was the second release of OpenSSL. So this happens currently. And so this is the motivation for tool for flexible TLS protocol executions and automatic fuzzing. Okay, so what we need, so we need a framework that allows us to execute flexible protocol flows. So for example, we can delete some message in the protocol flow. We can modify or duplicate some messages like client key exchange message. Or what we can do, we can execute message modifications. Below the encryption, so before the data gets encrypted, we want to modify, for example, padding in the application data, the application message. And afterwards, if we do it automatically, we want to detect the invalid behavior from the server. So if the server behaves incorrectly, we want to detect it, and we want to record the protocol flow that we just used and send it to the server once more for analysis. Okay, so this leads us to the TLS attacker and to the design of this framework. So we developed TLS attacker. TLS attacker is a framework that consists of several modules. At the heart, there is the TLS module, which implements the whole TLS crypto, protocol, messages, the workflow record, and so on handling. And we have some modules for attacks, for fuzzing, for transport over TCP or UDP, and we have a concept called modifiable variables, which I'm going to present now. And then I will give you some basic ideas why we use modifiable variables and how can we use it to adapt protocol messages and how can we build custom protocol flows. Okay, so the basics for TLS attacker is a concept called modifiable variables. So modifiable variables define basic data types like integers, bytes, byte arrays with some modifications. So the best way to introduce this concept is to give you an example. So imagine we have a modifiable integer where we set the value to 30. Then we set some modification like add modification to this integer. And then if we print the value, then we get a sum of 30 and 20. Okay, so this seems to be quite stupid and simple, and yeah, okay, it is. But this helps us to develop further modifications like sorting, shuffling, deleting bytes in byte arrays, and so on and so on. And we can use it in our protocol messages. So, for example, we developed the TLS stack, TLS messages, and we have here, for example, the client hello message, which consists of a list of cipher suites and the cipher suite length, and all these variables that we are using there are modifiable. This means that cipher suites are defined as a modifiable byte array, so we can modify them during the protocol execution, or cipher suite length, so we can increase, decrease the cipher suite length during the execution of the TLS protocol flow. These protocol messages are stored in a message list, in the list of messages, and for the convenience, they are serializable in XML. So what we can do now, so this is a basic protocol flow of TLS RSA handshake. So what we can see here, there is a client hello message defined in XML, then we have server hello, certificate, server hello done, RSA client key exchange message, and change subtract and finish messages, and at the end there is the application message. So this is the same protocol that we saw at the beginning of the talk, and defined in XML. So this we can use as an input to TLS attacker, and maybe it's now easy to imagine that we can now define new protocol flows. For example, if we want to duplicate RSA client key exchange message, we just duplicate this message, use it as an input into TLS attacker, and TLS attacker executes the protocol flow with 2 RSA client key exchange messages. We can remove the client key exchange messages, or we can use, for example, heartbeat message instead of application data. Now there was this concept with modifiable variables, and modifiable variables are also serializable. What does it mean? So if we have like heartbeat message, we can define the payload length in XML and define the integer modification. For example, add modification vary at the value of 20,000, and with this we just define heartbeat in XML without modifying core concept of OpenSSL or something like this. So there were proof of concepts of heartbeat attacks that modified cores of OpenSSL or other libraries. With TLS attacker, it's just a few lines of XML code that you can use to trigger a heartbeat attack. So you can easily write proof of concept attacks for this. Okay. So now, as you saw the concepts of TLS attacker and its flexibility, then you will probably believe me that it is easy to use it for fuzzing. So to randomly modify variables and to use it against the servers. So, but when we want to use fuzzing, there are 2 questions. So the basic question is, how do we detect invalid server behavior? So in our concepts, we use different TLS alerts. This is useful, for example, by padding oracle attacks, when we want to trigger a different padding behavior and observe whether TLS attacker gets a different padding, a different TLS alert. Or the other option used for memory detection leaks is address sanitizer. So we compile OpenSSL and C libraries with address sanitizer, and address sanitizer then is able to detect the memory problems, memory leaks at runtime as we fuzz the library. If the library like OpenSSL crashes, we record the XML protocol flow, and we can reproduce it and send it to the developers. Okay, so address sanitizer is available in recent compilers like GCC, and you can use it easily to compile OpenSSL or Botan or some TLS libraries. Okay, so if the vulnerability is found, we store it in XML and send it to the developers. Okay, during our fuzzing, we use a two-stage concept. It is currently implemented only for server-based fuzzing, but the concept works as follows. So we have in the first stage, we have crypto fuzzing for padding oracles, Bleichenbacher attacks, invalid curves, or poodle, or something like this. And in the second stage, we have fuzzing for boundary violations, which consists of 3 phases. So in the first phase, we do some variable filtering. So TLS protocol flow, as you can imagine, there are many messages, and each message contains many variables. So for example, client hello message contains a list of cipher suite length, client random extensions, extension length, and so on. So many variables. And we want to fuzz only the variables that are relevant to our attacks or that can cause crashes. So in the first phase, we just iterate over these variables and observe whether they introduce a new server behavior. So for example, if we fuzz the cyber suits, then the TLS server maybe changes the behavior, so it's good to fuzz it. Then we modify cipher suite length, the server verifies it and responds with a different message. So it's good to fuzz it. And then we go to client random message. The client random message is a random message. It consists of random bytes. And of course, it does not make sense to fuzz these random bytes because random bytes are always random. Okay. So, and then we can proceed as follows. So we filter the variables that are necessary for fuzzing. Then we proceed with filtered variables and execute random modifications like add, delete, XOR, and so on. We have specific included from other fuzzers like AFL specific values for example, integers like 0 or -1 that are used explicitly to fuzz integers. And at the end, we fuzz also in the third phase with invalid protocol flow. So we inject additional protocol messages in the TLS protocol flow and so on. Okay, so let's take a look at the demo. So as already mentioned, TLS Attacker is open source, so it's available at GitHub. You can clone it from the repository and compile it on your own machine. It's using Maven, but you can also grab the release that's compiled there. You can get some description of the basic attacks and so on, of the structure of TLS Attacker and so on. And some basic principles how to use it and how to invoke the protocol flows from Java or from XML and so on. There is also a wiki in there where you can get more information. There are also attacks described that you can use. So for example, Bleichenbacher attacks that you can invoke against specific server and so on and so on. In the recent time, I also implemented Lucky 13 attack that you can run against local server, and you get some nice pictures from this. It's a timing attack. So, okay. What I have now here is there is some old version of OpenSSL running, which was vulnerable to Heartbleed attack, and I have here now TLS Attacker. So first, what I do is I introduce some basic TLS protocol flow. So there is like client hello, server hello, and so on and so on. So if I use this message as an input into TLS Attacker, then I just simply run like Java jar client connect to localhost at 443 and execute this workflow as an input, which is located in test XML. If I execute this, then TLS Attacker executes the protocol flow against this message. You get the whole debug output, and maybe you can just take a look at Wireshark, and you will see that client hello, server hello, and so on will be used and against the server. And as I mentioned, then it is easy to define new protocol flows. So what you, for example, can do, you can take your RSA client key exchange message, you can duplicate it, you can save the protocol flow, and if you execute it once more, the protocol flow, then you will get unexpected message, and this is because we can see that in this case, we sent 2 client key exchange messages. Here's one, here's 2, here's the second one. Okay. And as already mentioned, you can also execute heartbleed attacks with the heartbeat extension. So as mentioned in the talk, you can execute some modifications. In this case, we had like 100 to the heartbeat payload length, and if we take it as an input, then this message as an input, then the server responds correctly with a heartbeat response, which is a bit longer. I will make it like to 10,000, so we can see more there. So if I make it to 10,000, then the server attempts to read 10,000 bytes, and it will respond with many bytes with zeros. So this is easy to execute heartbeat attacks. Okay. Good. So TLS attacker is open source, and you can use it as a pen tester or security researcher. Okay, let's get to the interesting part and to the results. So we used TLS attacker to evaluate specific servers and libraries, and we found padding oracle attacks in OpenSSL, Botan, and Matrix SSL. It's interesting that they were still vulnerable to these attacks. And then we found Bleichenbacher styled attack in Matrix SSL, and there were some other protocol flows like out of bounds read writes in OpenSSL and Botan library, or for example GNU TLS or OpenSSL did not check specific lengths of messages very well, and this could be used for insertion of specific data. Okay, so I'm not going to talk about everything, but I will just give you a brief overview of the OpenSSL vulnerability, which was the most interesting one and also motivates the work for TLS attacker. It was a padding oracle attack in OpenSSL, which was released in May this year. So let's get a bit back and introduce the padding oracle attacks and what is the reason to implement countermeasures against it. So a padding oracle attack works in general as follows, or exploits the following fact. So the attacker sends a ciphertext to the server, and it uses the server as an oracle that decrypts the message, validates the padding, and based on the padding validity, you get valid or invalid. This can be, for example, a different server error message or different timing. And it's applicable to AES-CBC. So the challenge in implementing countermeasures against padding oracle attacks is always to send the same error message. Yeah? This, of course, trivial. So we always need to send something like decryption failed or bad record MAC in case of TLS. This is, however, not everything what we need. We also need to have constant time processing. So there is also always has to be constant time padding and HMAC validation, and this was introduced in order to protect against the Lucky 13 attack in like 3 years ago. So if you implement these 2 points correctly, then you are not vulnerable to AES-CBC padding oracle attacks. Okay, so why is it important and how to implement this countermeasure? So how to implement it? So how AES-CBC in TLS works? It uses the MECT pad and encrypt scheme. And let's take a look at an example. So if we want to encrypt a message hello, then we end with the SHA-1 MEC. We need to proceed as follows. We need to have 2 blocks. In the first block, we put the message bytes hello. Then we compute an HMAC, which is 20 bytes long over the hello message, which should secure or protect the authenticity of the message. And afterwards, we need to pad the second block with some padding. So there are 7 bytes of padding, which is 66666. And this way, we can encrypt 2 blocks of AES, for example. Okay. So as I already mentioned, there is a challenge not to reveal the padding validity, so always we need to, there's timing problem, there's different messages, so we always need to do proper padding validation and MAC validation. This needs to be in constant time. So how do the libraries do this? So imagine, and what can go wrong? So imagine that we received this data that we decrypted with AES. There are two blocks with hello and so on. So what the server like OpenSSL does is that it takes the hello message and internally constructs an HMAC over this hello message and adds a padding by it. So it's some imaginary array that it's constructed internally, and then it takes this array and validates whether the decrypted data are equal to the masked data that we just produced. So we go from the right to the left and validate all the decrypted data whether they are equal to what we created internally. Okay, so in this case it is valid, then valid is set to true. Now imagine that the attacker just somehow flipped some bit in there and this padding is invalid, but we need to proceed till the end. So again, we create masked data and proceed from the right to the left, find out, okay, there's a difference, so we set valid to false and proceed to the beginning of the message, and not to reveal any timing information, we need to proceed till the beginning. Okay, what was the problem in OpenSSL? I will give you an example. So imagine we decrypted this data, so these two blocks are full of padding, which is also a valid case. So we have two blocks of valid padding 0f, and what the OpenSSL library does, it constructs a masked data with two blocks. It computes MAC data over the zero array and validates the data. However, it proceeds only to the end of the decrypted data. It does not check whether there is enough data to process HMAC and to validate HMAC, and it just proceeds with valid is true. So OpenSSL forgot to check whether there is enough data to validate the HMAC, and it set valid to true, proceed the TLS protocol flow. There was some integer underflow and responded with a different message. Okay, so what was interesting about this attack, that it was introduced by patching the Lucky 13 attack, which is a timing attack. So, and it was introduced only in one branch. So there are like 3 branches which implement CBC in OpenSSL. And in a branch which is used for AS and NI, this was vulnerable. This vulnerability was produced. So this vulnerability leads to a different server response. So, and at the end we could observe there is a record overflow or bad record MAC based on the padding validity. So what was wrong about this? So at the end, from a timing oracle which was introduced by Lucky 13 attack, we got a direct padding oracle that is much more serious. Okay, more information is on our blog post, and so if you are interested in why was the reason and what was wrong in the code. So this seems to be bad, so can this be even worse? So we constructed a timing attack, from a timing attack, a direct padding oracle attack. The answer is yes. So Matrix is introduced by patching Lucky 13, they introduced a buffer overflow vulnerability, and yeah. Okay, so now they're using TLS attacker in their TLS test suite together with some other libraries. Okay, so this leads me to the conclusions. So this talk is not an attempt to bash some crypto developers or maintainers, because maintaining a crypto library is hard. It's really hard. You can introduce new flows by introducing new code, new features, introducing new patches, and therefore systematic fuzzing and verification is needed during the development process. So a TLS attacker can be used for this purpose. There are other tools as well that are similar to this tool currently. TLS attacker is meant for researchers, pen testers, and developers to validate their proof of concepts or new attacks. And there is a future work that needs to be done. So better fuzzing, development of TLS client-side tests, better fuzzing strategies, and so on and so on. But this will be done in the future work. Okay, so thank you.